So finally, after almost half a semester, we're finally ready to talk about the normal distribution, the most famous distribution in all of statistics, the distribution you spent most of your time in your intro class last semester thinking about. And we're going to think about the normal distribution. We're going to get there in two different ways. We're going to think about it as the limit of the binomial distribution when n is large. But from the central limit theorem, we actually can think about it as the average of any distribution if you sample that distribution enough. So if you have some underlying distribution and you take the average of that distribution and you sample it enough, you end up with the normal distribution. So this is why the normal distribution is so central. It's the limit of many other distributions that you can sample, provided that you have a large enough sample size. So we've seen that the Poisson distribution is an approximation to the binomial distribution with a large n and a small p. And likewise, the normal distribution, we can think of it as an approximation to the binomial when n is large. So there's some math that shows this. You're not responsible for this math. So this is going to be a smart people tell us part of this class. But you can start with we recognize this as the binomial distribution, right? And then you just do some math. You grind through, and at the end of grinding through this math, you get to the normal distribution. So again, we can think of the normal distribution as just being the limit of the binomial distribution. So even though the limit of the binomial distribution when n is large. So even though we're not going to prove this math, we can demonstrate. We're not going to go through this proof in the class, although you're of course welcome to look at the proof on your own time. We can see very quickly with just a few lines of R that the binomial distribution is well described by the normal distribution when n is large. Right? So here I have our probability of success 0.5, probability of seeing ahead 0.5, like we've been seeing almost since the beginning of the semester. And just in this little snippet of our code here, we're going to walk our number of trials from 2 to 500. So we're going to flip the coin 2 times or 5 times, and what I'm showing here is 2 times, 8 times, and 36 times, right? And so in each case, we're going to plot out the binomial distribution. Those are going to be the dots, right? So this is going to be, so let's take this case of 8 trials here, right? So this is the probability density function that we've seen for the binomial distribution over and over again this semester. The probability of seeing exactly 0 heads, 2 heads, 4 heads, 6 heads, 8 heads, if you flip a coin 8 times, just given by dn by nom, right? So dn by nom 0 to 8, number of trials, probability of success 0.5, and of course the expected value is 4, right? You flip a fair coin 8 times, you expect to see 4 heads, so that's the peak of this probability density function. And these 8 points, or these 9 points going from 0 to 8, of course, because it's a probability density function, they'll integrate or sum to 1, right? So we can think of this as the binomial distribution, but if we think of the normal distribution as the limit of the binomial distribution as being the same thing, right? We can make lines here. So we've plotted out the points from the binomial distribution. Now we can make lines, and we can just count the number of trials going from 0 to 8. But now we do the d-norm going from 0 to 8, right? Where the mean is the expected value, the expected number of heads. So the mean is n times p, right? Because we know that the mean of the binomial distribution is n times p, and we know, a question that was on your midterm, right? The variance of the binomial distribution is n times p times 1 minus p, right? So I can just model this distribution of the expected number of heads as the normal distribution using now d-norm instead of d by nom. So d-norm running from 0 to 8 with a mean of n times p and a variance of n times p times 1 minus p, and we just feed in the standard deviation as being the square root of the variance. Now, the normal distribution is a little bit different, right? And you see this is a very good fit between the binomial distribution and the normal distribution. So it doesn't take very many flips of the coin until the binomial distribution approaches the normal distribution. And if we look here at 36 flips, it's basically a perfect fit between the binomial and the normal distribution. Now, there are some differences. The normal distribution is actually defined from negative infinity to positive infinity, right? So under the normal distribution, you can say, what's the probability of seeing minus 5 heads? Or what's the probability of seeing 27 heads or 1,000,000 heads, even though I only flip the coin 8 times, right? There's the normal distribution extends past this 0 and 8. Even if that doesn't make any sense in terms of flipping the coin, it's mathematically defined because the probability density function of the normal distribution is mathematically defined. Also, and this is important, the normal distribution is continuous and not discrete, right? So we can actually say what's the probability of seeing 2.5 heads or 3.75 heads. So this makes the normal distribution well suited to cases where you have not count data, not the number of flips of a coin, but continuous data. Right? And of course, this works for values other than 0.5, so I can make the same graph for 0.2, right? As I flip the coin more and more times, the expected value is now 0.2. The peak of this curve is going to be 0.2 times the number of flips, but the normal distribution still approaches the normal distribution is still the limit of the binomial distribution for some large number of flips. And it doesn't have to be a very large number of flips, right? Like, with just 18 or 20 flips, the normal distribution is getting pretty close to the binomial distribution. And again, because this is continuous, you can graph results intermediate to an integer number of successes, right? So the normal distribution is like we've seen. Count-based distributions like the binomial distribution or the negative binomial distribution make a lot of sense for RNA-seq experiments. But the continuous nature of the normal distribution makes it good for non-count experiments in genomics, perhaps most famously for microarrays. Now, of course, in R, we have, as usual, d norm, p norm, q norm, r norm. We don't have to go over these prefixes, but this is the probability density function, the cumulative distribution function, the inverse cumulative distribution function, and random sampling. And of course, we've been using random sampling all semester because the normal distribution is so useful. We've used this r norm quite a bit. For example, in our Metropolis walk, right, we were using the next guess from old pi to new pi in the Metropolis walk. We used the r norm for that. So the probability density function, if you go back to the math that's described on this web page, and you take the limit of the binomial distribution, at the end of that math, you end up with this formula. This is the formula for the probability density function, right? So there's some constants here, right? So this is the standard deviation. So it's the square of the variance. The square root of the variance. This is the variance itself, right? So you have some function that involves the variance. Raised to this x minus u squared, right? This is each value of x along the x-axis that you're trying to evaluate the normal distribution for. This is the mean, and this is the variance here. So this probability density function is defined this way, and that's the math that you get to at the end of this assumption of the binomial distribution. So we've seen QQ-UNIF earlier in the semester, which gave you the quantiles for the uniform distribution, the expected value for the uniform distribution. So there's likewise into R is built QQ norm, right? So if I just say A dist equals R norm 1000, okay. So remember this R norm 1000. Actually, if we flip into R for a second here, and right, if you type R norm 10, right, that's sampling from the normal distribution with a mean equals to 0 and a standard deviation equal to 1. Right, so I'm just, this R norm is just sampling from the uniform distribution, from the normal distribution with a mean equals 0 and a standard deviation of 1. And if I couldn't remember what the default values were, I can pop up the documentation for R norm, right? And so right for R norm, if I don't specify a mean and a standard deviation, I'm going to get a mean of 0 and a standard deviation of 1. This is going to be called standard normal distribution, a standard normal distribution with a mean of 0 and a standard deviation of 1. And this standard normal distribution is going to be very important because it's going to be what we sample from the chi-square test. And for the chi-square distribution, the standard normal distribution is what we use for the chi-square distribution. We build on the standard normal distribution to make a chi-square distribution. And the chi-square distribution in turn is what's used for the t-distribution, which in turn is what's used for the t-test. So this standard normal distribution is going to be very important, and we're going to spend some time developing ways to think about that standard normal distribution and how we can transform any standard normal distribution or any normal distribution into a standard normal distribution. So in this line of code in our PowerPoint, when we say R norm 1000, we're sampling from that standard normal distribution with a mean equal to 0 and a standard deviation of 1. We throw that into a vector called A dist, and I can now make a test of normality by saying QQ norm A dist and QQ line. QQ norm draws the points, and QQ line draws the lines. So we can ask, how well does a particular set of data match our expectation of normality? And you guys will remember, and we'll go over in great detail in the coming weeks, that this assumption of normality is central to most standard linear models. So if you have a linear regression, the assumptions of a linear regression are linearity, independence, normality, and equal variance. This is a test of normality. And if you're close to the expected values under normal distribution for your actual distribution, then your data are normally distributed. And we can easily make a distribution that violates this assumption of normality, right? So I can say a dist rx 1000. So now I'm sampling from the exponential distribution, right? And so if I say, is the exponential distribution normally distributed? It's not, right? So the exponential distribution is a different distribution. And so this is not sampled normally. So this is going to be, again, important for when we test normality, and we're going to be wanting to test normality quite a bit because the assumption of normality is central to most standard linear models. And this is just the documentation for this exponential distribution. And of course, we're familiar with the exponential distribution in our class because we used it as our prior for one of the homework assignments for the Metropolis algorithm. Of course, the documentation for quantile plots is often online. This idea that the normal distribution is not just the limit of the binomial distribution, but actually, somewhat amazingly, is the limit of any distribution if you take the average of that distribution and sample that average with independent and identical sampling, and that's actually called the central limit theorem. Right. So when you take the mean of any distribution that you want, you take the mean of that distribution, and each sample in that distribution comes from a distribution with a constant mean invariance, where the samples are independently identically distributed. And it turns out the central limit theorem says, and this is sort of a remarkable result, that no matter what distribution you start with, if your sample size is big enough, you're going to end up with a normal distribution. So we won't show the math for that. You can go to the wiki page to prove that. So this is going to be another smart people tell us. So smart people will tell us that this is true, that we approach this limit, but we will demonstrate this in R, right? So here I have some distribution, right? So I just have a regular expression, an exponential. It's funny that I thought that was regular expression. This is sampling from the exponential distribution, right? So some distribution that's not a normal distribution, right? I'm going to sample this 10,000 times, right? So here, I again, using R with my heavy Java accent, I could have just said some dist 10,000, but here I'll just, with a for loop, I'll just, using somewhat sloppy R, just make my results hold 10,000 poles from this exponential distribution. Okay. So I do this, right? And so I've been sampling the exponential distribution 10,000 times. I make a histogram and I plot that histogram here, right? And so here we have this nice exponential distribution, right? So when I plot the histogram of this exponential distribution, I have the exponential decay, right? When I ask to say, is this exponential decay normally distributed? The answer is no. The exponential decay is not normally distributed, right? So if I try and fit this exponential decay with a normal distribution, right? So I try to plot the exponential distribution with dnorm with a mean of whatever I pulled from the exponential distribution, right? So I say just the mean is the results of these 10,000 samples of the exponential distribution, and the standard deviation is the standard deviation of this exponential distribution. This doesn't fit particularly well, right? So if I do this in a histogram, this is the best fit to a normal distribution of this exponential decay, right? And the shape of the normal distribution is not close to the exponential decay. And likewise, if I use the QQ plot that we just saw to ask, is the results of this of pulling 10,000 results of sampling the 10,000 results of sampling the exponential distribution once, the exponential distribution is not well fit by the normal distribution, right? The theoretical quantiles under the normal distribution are not the same as what we saw for exponential decay, because the exponential decay is a different distribution than the normal distribution. But if I just make one change to this code, right? Or two changes to this code, really. So the first change is, instead of just sampling the exponential distribution once, I sample it 1,000 times, right? So Rx1, right? We go to our Rx here, right? If I say Rx1, I'm sampling the exponential distribution one time with whatever the default parameters are. If I say Rx 1,000, right? I'm sampling that exponential distribution 1,000 times, okay? And then what I'm storing as my data is the mean of those 1,000 times, right? So I'm sampling the exponential distribution 1,000 times, and then I'm storing as my data the mean of that distribution 1,000 times, right? And so now when I do that and I make my histogram, the average of the exponential, remember the exponential distribution is not well fit by the normal distribution, but the average of the exponential distribution is very close to perfectly fit by the normal distribution, right? So this is the average of sampling the exponential distribution 1,000 times, right? And the mean and standard deviation of this are almost perfectly normally distributed. And when I look at my QQ plot, I get a perfect normal distribution. So this is an example of the central limit theorem. The central limit theorem says that whatever your distribution is, if you take a large enough sample size of that distribution and take the average of that distribution, the limit of that is the normal distribution. So that's the math that we're not going through to prove that, and that's the central limit theorem. So what the central limit theorem says is that the mean, and if you take identically an independent distribution of a mean from any distribution, from any underlying distribution, you'll eventually get a normal distribution. But what the central limit theorem, which is unfortunate for biology, so unfortunately for biology, what the central limit theorem does not say is that your particular data set is normal, right? So there's all kinds of data sets that we have in biology that are not normally distributed, and this is because sometimes we're not taking an average of an underlying distribution. Maybe we are, but our sample size isn't sufficient. Maybe this idea of independence is not well met by biological data sets, so maybe act into something different in patient X and patient Y, so you just can't average across patient X and patient Y in order to get a single value. So even though the central limit theorem seems to say that most data sets should be normal, in biology, again, unfortunately, data sets are usually not normally distributed, and this potentially leads to some problems using linear models, which we will see over the next couple of weeks. So this idea of the standard normal distribution is very, very important and central to all linear models. So we're going to spend some time thinking about the kinds of manipulations that you can do to any distribution, any normal distribution, to turn it into a standard normal distribution. So we're going to define some rules about what happens when you add or subtract constants or when you multiply or divide by constants. So here I start with 1 million data points, and I sample the normal distribution a million times. And here I'm not in standard normal form, right? I have a mean of 50 and a standard deviation of 5, right? And so I make a histogram, the mean is 50, the standard deviation is 5, and this is what this looks like, right? And the mean of my vector of 1 million data points is very, very close to 50 by the law of large numbers, because 1 million is a large number, right? So one of the rules that we want to learn is that if you add or subtract to a constant to a normal distribution, the distribution is still normal, right? So here, right, I'm going to center my data set at 0. So remember, the standard normal distribution has a center, the mean is 0, the standard deviation of 1, right? So it's a pretty straightforward manipulation to center a given data set at 0 by just subtracting off the mean, right? And so the idea is that when I subtract off the mean, so here I have my data set of 1 million points, and here I've just subtracted off a number very close to 50, and what I get is a number that's within round off error of 0 here, right? And so the idea here is that I've taken this entire distribution and I've just shifted it along the x-axis, so now that it's centered at 0. Okay. And so when I take a distribution and I add or subtract that distribution, it's like in some ways it's like I haven't even touched the data. I've just taken the x-axis and moved that along, right? I've picked up the entire distribution and just dumped it on the x-axis, and by subtracting the mean, I've centered it around a mean of 0, right? And likewise, and this is going to be important, if we divide or multiply a normal distribution by a constant, the underlying distribution is still normal. So it's going to turn out that in order to make a standard normal distribution, the trick is going to be to take the distribution that you start with, subtract off the mean, right, and then divide by the standard deviation, and what you're going to end up with is a distribution where the mean is 0 and the standard deviation is 1. And this is a transformation that's going to be central to everything that we're going to do, because, and actually if you think about it, this is the form of a t-test, right? You're dividing, you subtract off a mean, and then you divide by some, not quite the standard deviation, because we have to correct for sample size with standard error in ways that we'll see in the next lecture. But this idea of sort of subtracting two means and dividing by some function of the variance is going to be the format of the t-test, right? And you can sort of almost think of that as taking your data and putting it into standard normal form. So we're going to go into this in much more detail in the next lecture, but I wanted to sort of plant this idea that what we need to do is subtract by one constant, the mean, divide by another constant, which is the standard deviation of this data set. And what you end up with is a distribution that is essentially in standard normal format. And again, so just to say this again, because we're going to be doing this operation over and over and over again in the next few lectures, right? We have some data, we want to put it in some standard normal format. We subtract the mean, divide by the standard deviation, and we're going to end up with a mean of 0 and a standard deviation of 1. And again, this is going to be super important because the chi-square distribution, which is used both for the chi-square test and as part of the t-test, right? That distribution is the sum squared of normal distributions with this mean 0 and variance 1. So this transformation of data to get it into a mean 0 and variance 1 format is going to be important for tests that rely on the chi-square statistic, such as the chi-square test and the t-test. And then this chi-square statistic itself shows up in the t-statistic, t-test, the t-distribution, which is used for the t-test, right? Where we have, again, we see this z here is this normal distribution, again, with a mean of 0 and a variance of 1. Of course, if the variance is 1, the standard deviation is 1. It doesn't matter whether you say 1 or the square root of 1. That's the same thing, right? So this standard normal distribution shows up in the numerator in the t-distribution, and then this chi-square distribution, which itself is the sum of standard normal distributions, shows up in the denominator of the t-distribution. So the standard normal distribution is important for the t-distribution, both for the numerator and denominator. And of course, as we argued in the previous sub-lecture, right, this t-distribution is important for the t-test, and the t-test is your go-to statistic for many analyses in bioinformatics and biology. And as we argued in the previous lecture, the t-statistic, the t-test based on this distribution is actually one of the most robust and generally useful statistics in genomics. But we're going to look at that in a fair amount of detail in upcoming lectures. In the meantime, if you're done with this lecture and waiting for the next ones to post, you can review the t-test and chi-square test from your first semester stats book.